today. And he's been mostly at Waterloo, but we're glad that he stopped in on us in Toronto, and he's going to tell us about the dominant energy condition for smooth metric measure relativity.
So thanks very much. Pleasure to be here and to see several old friends. And so basically this talk is really kind of a research in progress talk. Maybe to some degree I'll be talking between myself and Argam, because it's a project that we've had. We're working with Eric Ling, and as I say, it's in progress and it changes from week to week. So we'll see how it goes. Yes, I know. So so once again, I find myself talking about smooth Bakry-Émery curvature, which I have sworn several times I would never talk about again, and I've sort of stopped. So, but here we go again. I think it's been. I think the last time I gave a talk here that was not on this topic was 2017. So let me see if, unfortunately, when I look at the screen, I can't, it doesn't mirror. So, so the first thing I'd like to mention is what it is, which basically, so I prepared the slides just in case there was an audience that was not familiar with differential geometry at some degree. And I'm sure you all are, so I don't really need to tell you about the Riemann tensor, nor the Ricci tensor, which is its trace. But I do need to mention the Bakry-Émery Ricci tensor, which is augmented by a function, which we won't pin down. It will just be something that you can give. And I will augment it with two terms, a Hessian term, which pretty much everyone who does this has, so everyone who does it definitely has, and one other term with a free parameter m, which is often called a synthetic dimension. So now, the general case is not just to augment it with this function. I guess it can be fancy and use the pointer, yeah. But instead to go to the non-gradient case where the function is replaced by an arbitrary vector field. I've put the sharp on because it's a vector field, but of course I want to lower the index, so to speak. I want to use the dual field. I will probably ignore that throughout the talk. It's only there for this one slide. This comes up probably in my next slide. I've got more explanations to why it comes up. I believe I do. So yes. So the gradient case comes up in all sorts of phenomena that are of interest to people here. Example being in Ricci limit spaces, where the F comes from the density belonging to a measure that's absolutely continuous with respect to the Riemannian measure. So it appears in optimal transport, which everyone here knows more about than I do. But, oh, forgive me, I've just pushed the wrong button. Here we go. And I guess I should say simply spaces rather than manifolds. It appears also, though, in warp products in Riemannian geometry and in what physicists call Kaluza-Klein theory. So, the general case, which we had on the slide a moment ago, where the vector field was not a gradient, shows up basically in Riemannian submersions, or shouldn't say Riemannian submersions because they show up in space-time, but they show up in the near-horizon geometry of Killing horizons, in particular in general relativity, and that's a bit of jargon for saying black holes. So this arises in, oh, I got to get used to this. So this arises in the study of black holes as well. Now, as I say, I prepared the slide not assuming that there was background in differential geometry for everyone. So for most, perhaps all of you, forgive me if I just go through this. Basically, I have to sort of recover myself and see exactly what I wanted to tell you about this. Basically, the Ricci curvature, you can think of it as, you can think of the equation that I'm showing you right here as the definition of Ricci curvature. Roughly speaking, let's take the so-called mean curvature H to simply be defined as the logarithmic derivative of a Jacobian determinant. And again, the wrong button. I think it's the clicker, it's not me. So what I'd like to do is to draw, in this case, I'm in flat space, so I'm drawing straight lines. In general, I'd be drawing geodesics. I'd like to think of them as transporting an area element along the geodesic. And again, I'm going to give up on this pointer. So again, as they transport that area element, it is just an identity, really the definition of Ricci curvature, that the evolution of the area element obeys the differential equation that's sitting here in the middle. I will try. I'll risk it. Let's see. Okay, I have to keep my thumb well away from the other button, and then I think it works. So this equation right here can be considered, you can ignore the last slide and consider this as your definition of Ricci curvature in the t direction, and I've used the subscript t to indicate the Ricci curvature takes two vectors as argument, and I want to take the tangent vectors to these lines along which I'm parallel transporting. So in a flat space, that term wouldn't be there. In a curved space, it is, and so I've drawn down below a now it just doesn't point where I'm pointing. So I've drawn down below the a sphere, and what will happen to this little area element as it moves along a sphere, and then you have a non-zero contribution there. And in particular, if the Ricci is bounded above by a constant, which I've chosen to write here as negative c, and in fact, of course, on a sphere, Ricci is constant. Bounded below, thank you. Then the equation that I've written right up here just becomes this. In general relativists have a habit of calling this equation, although it's really not an equation anymore, inequality, the Ricci equation. So it's just a Riccati equation, a scalar Riccati equation. Runs by both names, but I'll typically name it, it needs a name. And the name Ricci is about as justified here as any other name gets justified in the field, which is to say it's not very justifiable at all, but nonetheless. So, okay, so there it is. So I think I've just got a little exercise here in going through the calculation that basically positive curvature is basically positive curvature and concavity connect to give you something that to let you learn a little bit about the geometry. And so here I impose the curvature bound. Let's go through it. Then with the curvature bound from the slide before, which, as I say, that equation is really a definition of Ricci curvature, nothing more. Then we get this inequality. And so I teach introductory differential equations to engineers. So this would be like my first lecture. It's separable. So I've just divided through like this, so we can integrate that. Right, so you can simplify this. The left-hand side, of course, it's just the derivative of 1 over h. Now I've pushed something else and a little hand icon came up. So we can integrate that given an initial condition. And there's the solution that 1 over h grows linearly. So let's put in some initial concavity. So we're on that sphere, and we've started at the bottom, we've come up, and we've gone past the equator. So we have a little bit of initial concavity. That logarithmic derivative that I showed you before is now negative. So that's what this statement says. Then, lo and behold, the right-hand side is going to vanish because this is negative. The point's wrong. This is negative. This will be positive. We start at t equals 0. So there'll be a 0 in there somewhere. And when there's a 0, of course, h will diverge, in fact, to minus infinity because you're approaching it below. So the thing will blow up. And you saw that on the previous slide. That was just that area element shrinking to 0 as you came to the north pole of the sphere. So it's just a general property, has nothing much to do with the sphere, except that it just comes from the Ricci curvature bound and the initial concavity. Okay, so now I want to define, now I want to use the Bakry-Émery Ricci curvature. And I'm guessing that the next slide will explain why. Sort of. Go back for a second, perhaps. Right, so if I go back for just a second, I have two terms here that I'd like to justify. This one, the justification's coming up, and then this one will be a little more ad hoc, but we'll see. Okay. So I'd like to tell you that really all we're doing here is what physicists call Kaluza-Klein theory and what Riemannian geometers call warp products. So I've got a warp product metric here. What I really am thinking of in the Riemannian metric, of course, what I'm really thinking of is a product of two manifolds. And the Riemannian metric is just the product metric on the manifolds with a function in here. And the function depends only on the first manifold, not on the second one. Then if you compute the volume element of the whole thing, it basically splits like this. Little m should be the dimension of the second manifold. Otherwise, you'll get a factor, the dimension will appear in the volume element. And if you compute the Ricci curvature, then the projection of the Ricci curvature onto the, got too close to the wrong button. The projection of the Ricci curvature onto the tangent space of the first manifold will give you the Ricci curvature of the first metric plus, lo and behold, that Hessian. And this term, oops, now the clicker doesn't do it at all. So this gives rise to the Bakry-Émery Ricci curvature of G1. That's basically just where it would come from. Yeah.
So I mentioned scaling. So F over M, that's invariant of the change, right?
F over.
So so why is that the case here?
What?
Because the Hessian doesn't have M.
Oh, right. Well, I didn't quite understand the question though.
Well, like if you take F times 2, then take little m times 2, that doesn't change the metric G. But then this Ricci of G.
Yeah, this is, but I've got,
But he's fixed,
this is G1.
He's fixed M to be the dimension of M2. So you can't scale M with it.
That's
Oh,
true. Thanks. Oh, yeah. No, quite right. Actually, indeed, that's exactly why I chose that. Otherwise, you're quite right. It's not going to scale correctly now. Now I see what you were getting at. Scalar curvature is sitting down here, and this is going to show up again later. And so the scalar curvature gets this extra term, and then lo and behold, it gets these terms coming from. They don't entirely come from the Hessian. They are not just the trace of this. The reason it's not just the trace of this is I didn't show you the other component. The components in the G2 direction, the projection, and they contribute, of course, to the scalar curvature. Okay, so this comes down to energy conditions. Singularity theorems in relativity use a few of these. Strong energy condition. Here I have written it in the somewhat incoherently. The singularity theorems usually, of course, are just phrased for the ordinary Ricci curvature, but you can also prove them if you make an energy condition assumption on the Bakry-Émery Ricci curvature. And this shouldn't surprise you, because if the singularity theorems hold, say, in four-dimensional general relativity, why would they not hold when you do a warp product, you add on a little extra piece? So this would be the strong energy condition in the Bakry-Émery sense. By the way, the ordinary sense is usually denoted by m equals 0, which makes no sense because you're dividing by 0. You have a 1 over m. But then the only way you can make sense of that is if the function f were taken to be a constant. So then it just reduces to the usual Ricci curvature. So that's the convention. So with this condition, you can prove singularity theorems with in relativity. With the null energy condition, you can also prove singularity theorems. And Robert has a very nice reformulation of that null energy condition. Two energy conditions that don't, to my knowledge, appear in the singularity theorem, but if someone knows of one, then point them out to me. The so-called weak energy condition, sitting in the middle line, and the dominant energy condition, which is where I'm eventually going, which is that the so-called Einstein tensor of this combination, evaluated on two future time-like directions, could be future causal, or two past time-like directions, but either both future or both past, then that's positive. And I'll give a version for this. I've given the top ones in the Bakry-Émery formulation. This one I've just given in the m equals 0 formulation, but we'll will give it, and it's the obvious answer. You can guess in advance, but I did not guess in advance what it would be. So I did mention that you can prove these things using those conditions. You can prove singularity theorems using those conditions. Jeff Case proved the Hawking-Penrose singularity theorem. There are three very classical singularity theorems of relativity that show up in the Hawking and Ellis book. Myself and Greg Galloway, we proved the cosmological version of the singularity theorem due to Stephen Hawking. We only did this in the case where we didn't have that M term. In other words, we took M to be infinity, so we did it in that particular case. But then with Will Wiley, I extended it, and nope, wrong button. I think if you double click, let me just try this. Yes, if you double click the pointer, it advances the slide. So if I click the pointer too often, then it advances the slide. That's my problem. All right.
Sorry, the N here is the total dimension.
Oh, right. The N is the dimension of the base space, I think. In fact, yeah.
Sorry, the base space is M1 or it's M1?
It's M1. So N is the dimension of M1. Okay. And so one last remark about them is that they use, just like I mentioned a moment ago, you really need to combine this with an initial convexity or concavity condition. And that gets augmented by an F term as well. And we'll see if that appears on the next slide. It doesn't. It's the mean curvature. I think actually it was a slide. It's in there somewhere. I may have just gone through it. That's the mean curvature on the Cauchy surface, augmented by the gradient of F in the time-like direction with a minus sign, as it turns out, in a normal time-like direction. And it's sitting on one of these slides, but whether it's in the future direction or the past direction, I'm not sure. Okay, so the dominant energy condition. I've actually got a preview of this down here, but I haven't been paying attention to it, and I really should. So forgive me, I'll catch up to myself, and that way I'll know what's coming in the future. Right. So so there it is in relativity, and in this Bakry-Émery setting, I claim that it should be what's in the middle of the slide. And the main point is that I claim that the scalar curvature should be this, and that is not the trace of that Ricci term. And you can see that that should be the right thing, because if you regarded this as a warp product, then that would be what you would get on the projection into M1, the base space, as I've been calling it.
Sorry, it fails to be the trace because the factor 2 and the factor of F+1 is there.
Right, both those things. And the factor of 2 is probably more of a nuisance than the factor of M+1, but yes, for both those reasons. And I should, of course, emphasize here that if you're thinking this is a warp product, then M is a positive integer, but there is no reason in general to set M to be a positive integer. You don't have to think of this as a warp product. M can take any real value, including negative real values. Okay. And a little note on the bottom that I probably should tell you about. This condition descends from restricting the dominant energy condition to the work product. Oh, yes, when this is scalar flat, and that's because I've dropped that R is the R of R1 of G1. And you might remember from a slide a little while back that there's also an R of G2. I've dropped that. I could have kept it with the sign condition. I don't need that it should be 0. I need that it should be 0 or I think negative. But I could have, for what I'm about to say, I could have just replaced that with an inequality. We'll take it to be scalar flat for the remainder. All right. So as I point out, these two things are different, the trace of that and this guy up here. From Gauss-Kadatsky, if I'm in a space-time and I'm on a so-called moment of time symmetry, so I'm on a totally geodesic space-like surface, Then in Gauss-Kadatsky, you might remember that it has several terms that are the extrinsic curvatures, the second fundamental forms of whatever surface you're dealing with. That'll be 0. And Gauss-Kadatsky then reduces to the scalar curvature of your submanifold being just this combination. That combination is the Einstein tensor, and that's basically how the dominant energy condition comes into play in relativity considerations. So in the standard, with the standard, say, general relativity, then this implies that then dominant energy implies positive scalar curvature on a submanifold. In this case, I'm thinking of a hypersurface, space-like hypersurface. Now, the Riemannian positive mass theorem assumes precisely this. When that scalar curvature is positive, you don't have to think of this as a submanifold anymore. Think of this just as a Riemannian manifold, although it really is a hypersurface in a space-time. Then the ADM mass, the Arnowit-Desser-Misner mass of that slice is greater than or equal to 0, assuming asymptotically flat conditions and so forth. So Baldov and Ozuch proved a weighted positive mass theorem, in other words, a Bakry-Émery Ricci positive mass theorem. And they assumed they had the m equals 0 case, but they assumed that this particular thing be positive. And that's so that's where the 2 is important, but they assumed this. Their weighted mass, which I think is coming up on the next slide. So here's their theorem, but never mind the preamble. That's just all the conditions that you need. Their weighted mass is sitting down here. It's the standard ADM mass of relativity, and then an augmentation by the gradient of this F with a weight in there. In case you haven't seen the ADM mass, the formula is on the next line, and of course it's rather ugly, but that's the definition of the ADM mass. You take a very large sphere at infinity, and you measure this quantity. And this should roughly, you can think of it in sort of Newtonian terms. This is like the gradient of a potential. It basically picks off the mass enclosed in that large sphere. So they have an augmentation, and lo and behold, when they assume that this is greater than 0, then you get positive, whoops, clicked it too fast, positive weighted mass.
So this is for when?
2022, I believe. I recall looking at it while I was here. So I believe 2022. Now it's easier than you think, or unless you think it's easy already, because it is just the Witten theorem conformally transformed. And the reason I remember talking about this in 2022 is that Ahil Elahi visited, and I said, oh, we should look at this. And Ahil said, well, it's nothing. You just conformally transform the standard theorem. And of course, it is nothing, because really, when you think of a warped product can be rewritten as a straight out Riemannian product times the conformal factor. It's conformal to a straight out Riemannian product. So after you do the conformal transformation, you just got a Riemannian product, and you got the positive mass theorem on the base. Adding on those extra dimensions does nothing. And so after they were published, this was realized. I think even they eventually realized it. I should add a caveat in here that the Witten theorem, I've been talking about Kaluza-Klein theory quite a bit, and it happens to be true that the positive mass theorem fails in Kaluza-Klein theory, and Ed Witten pointed it out. It fails in a particular and very subtle way. It doesn't, Witten's theorem is based on spin structure. It fails for warp products that admit spin structure, which is sort of surprising. You expect maybe it'll fail for those that don't, but they admit basically the wrong kind of spin structure. You have to have a solution of the Witten equation, which gives you a covariantly constant spinner, a parallel spinner at infinity. And the example where it fails is that, roughly speaking, it fails. It's rather hard to do this in performance art. It fails on the kind of manifold where the topology is such that if you know something about spinners, you know you do a 2 pi rotation and the spinner flips sign. But you can do that in the middle of the manifold. You can also propagate out to infinity, do it, and then propagate back in. And it fails when you don't get the right match up there, when the asymptotic conditions are such that if you propagate around a circle at infinity, the spinner does not flip sign. And so there's a very nice example, but these warp products are not of that kind. So they don't, that particular example, I guess you can think of it as a suspension, but you can't think of it as a warp product. The warping factor degenerates to 0. And so, so you do get a theorem in this case. Okay. So I'd like to modify the dominant energy condition. As I say, this is work in progress, and the goal of the work keeps changing because of, well, various reasons. We were mostly, you start to calculate and you realize it goes in a different direction. So this is with Agam, who's present, and oh, I clicked it too fast again. Eric Ling. Do I need to tell you? Oh, right. So where this has been going for the last 2 weeks has been toward a horizon topology theory, which turns out to be one of my favorite subjects. So that should not be a great surprise. So let's see. Got the theorem here in one version, and I hope it's a theorem because, as I say, it keeps evolving week to week. So here I've got an n+2 dimensional space-time. Why have I got, I can't remember why I fixed the dimension to be 2, and I have to be careful with typos because this is just in the last couple of weeks, but let's see as we go through it. So I've defined the warp product. Oh, I think I see why I fixed n. I've defined the warp product as follows, and I've assumed that it will obey, in this case, the dominant energy condition on the warp product, and so that'll descend to the Bakry-Émery dominant energy condition on the base manifold. I don't think I need n to be 2. I think it should be n plus m. In fact, I'm sure it should be n plus m. So in this setting, I'm going to assume a black hole horizon in the following sets. I'll assume a so-called marginally trapped, it's this line right here, compact marginally trapped codimension 2 spacetime. Oh, maybe that a spacetime surface. Maybe that's how the 2 got in there. We'll see if it needs to stay, if that should be M. So on that surface, maybe I'll draw. So I'm just assuming I've got a spacetime sitting here like this, and I've got a little codimension 2 surface, and I'm not thinking, here's my spacetime. Then this should sort of resemble the codimension 2. And I'm thinking of the outbound null direction from that surface. And I'm going to denote that with L. And I want my function f to not be increasing at the surface, which we're calling sigma. Okay. So I need that on sigma, this quantity. I won't use the pointer if I can use my fingers. Then I'll need that quantity be less than or equal to 0. I claim that if we're in, if the dimension of this, I think that's where the 2 came from. I claim if the dimension of sigma is 2, then this is diffeomorphic to S2 or T2, and I think we can rule that out, but we haven't yet. If n equals 3, then it's diffeomorphic to either spherical space, which is an S3, perhaps modded out by identified by a discrete group, or tori. And again, I think we can rule everything out except the spherical spaces, but we haven't done so yet. The 2 on the bottom are conclusions. In fact, what you'll get is a non-negative scalar curvature metric on the base space, and then these follow from that. So, okay. Remarks on black hole topology. So theorems about black hole topology come in 3 types.
So this sigma is already a smooth manifold, right?
Yes.
It's assumed to be smooth.
Yeah, smooth. Yeah. So remarks on the theorem. There are three types of so-called black hole horizon theorems that come from three notions of black hole horizon. The first notion is that really it's a theorem about the topology of the event horizon. Those are called topological censorship theorems. And let me explain. Again, perhaps a little diagram will help. If you've seen a conformal diagram in relativity, this may help. And if you haven't seen it, this is just going to make things worse. So I am drawing the conformal diagram of the Schwarzschild solution. It looks like this. What this really means is if you travel along, say, travel at the speed of light, let's say to make things simple, and you do it for an infinite amount of time, you're not going to end up in the black hole, which is here. You will escape to infinity, which is here, often denoted, by the way, with a scribe plus, if you've seen the notation. And so everyone who escapes to infinity can look back at their histories, and they will see all of this. But they'll also see a boundary here. And this boundary is because someone has fallen into this region, and then they can't escape. They hit the singularity. And that wavy line is meant to, you take the page and you rip it. That's the singularity right there. So this boundary is the event horizon. And if you want to know the topology of that, there are topological censorship theorems. The kind of topology theorem that I'm dealing with here, and it was first proved by Hawking in, I think, maybe 73. And then Galloway and Shane used the same approach in later work. It deals with marginally outer trapped surfaces. That's the acronym there. And a case of those, which is called an apparent horizon. And so the difference is this is a boundary. If you happen to be in n plus 2 dimensions, which we were a moment ago, a boundary has n plus 1 dimensions. An apparent horizon is a cross section. So it has n dimensions. So I'm looking at a cross section of that thing. Now, what I need for this cross section is I need the concavity. I need a geometric property. The property that I need is that the outbound geodesics, remember they drag along a little area element, and that has a Jacobian determinant, and I need that logarithmic determinant way back in the first slide, logarithmic derivative, be non-positive. So in particular, for a so-called apparent horizon, it's 0 for the outbound direction this way, and it's negative for the inbound direction like that. My way of visualizing this is you're sitting on some kind of a ball of light, you know, a fluorescent surface, and you've lit the match and it's all exploded simultaneously. Outbound geodesics go that way, outbound light goes that way, inbound goes this way. But the gravity is so strong, the inbound comes in, but the outbound also comes in, or at least in this case, does not escape. It just goes up marginally. That's what this theorem deals with. And lastly, there's something called Killing horizon topology, which we won't bother with today. Is that my phone? Oh, no.
Extreme black holes there.
It's mine. Let it ring. It's over in my bag. Yeah.
Extreme black holes, does that refer to like the Kerr solutions for the extremal values of the angular
Yes.
momentum?
I think that's the last time that I think that ringing was, no? Technology.
So it's also your slide.
Oh, sure.
This is a stationary space.
Do I have to be in a stationary space? No, I think no, not in general, no. So there are versions. That's right. The apparent horizon can be inside the event horizon. It's not necessarily on the event horizon. Okay, oops, is that the wrong direction? No, that's the right direction. That's where we're, okay, but so let's give the theorem in one more kind of language. So here I've put it in the language of smooth metric measure. So here I'm just ignoring the what product structure. I don't have it anymore, in fact. And so if I don't have it, I just have to assume this, which would have earlier been the curvature on the base space. Now I'm just considering it to be Bakry-Émery Ricci curvature. So this is my dominant energy condition. I don't think I need to tell you anything more about this. As I say, I want to get rid of these tori and so forth, and I think there's an argument of Galloway that gets rid of it, but we haven't had time to do it. The tori and the connected sums. If you look at Hawking and Ellis, like 1971, the theorem in there says you can get rid of those. It's gone. And it turns out that it took until 2008 for Galloway to actually prove that you could get rid of those. So,
So we see, there's also recently theorems about, and Bray and Semela have these theorems about blowdown limits of things where you get these kind of classifications. Is there any connection?
Bray and
Sorry, Rouet.
Bray, okay.
Semela.
Oh,
These theorems about blowdown limits, where you look at the asymptotic growth at infinity of Ricci lower bounded manifolds or Ricci lower bounded metric measure spaces.
Yeah.
And they again get classifications.
Mm-hmm. Yeah, take a look later. Okay, I guess I'll say a few words about proof technique because I have a few minutes, but I will try to make it relatively painless. The basic idea is that the thing I've drawn over the, well, not the thing I've drawn right there very badly is really, at least if you are in a stationary spacetime, let's be stationary now, then it's a, if you're in a static spacetime, it's a minimal surface. So if you're in a spacetime where, like Schwarzschild, where nothing happens in time, then these apparent horizons are actually minimal surfaces. And I've drawn two, one stable, one not. The apparent horizons should be stable. So the terminology, I think most of you will already know the terminology of minimal surface is only accurate. The surface area is minimal if you do a perturbation of the surface that has fairly limited support. Not necessarily, you know, if you make a little bump on the surface, it's minimal. But of course, if I deform the entire surface down here, I can make a smaller surface just by pushing along. Not true with the stable one. Any push of the stable one will make a surface that's at least as big, if not bigger. And apparent horizons do really the same thing, even in general, although there's a bit of a subtlety in general. So our theorem is of that type. So you look at the so-called stability operator, and this tells you about the first order perturbations of the area if you push forward or push back. And for whatever it's worth, there it is. And you get no information about this at all, except that you see a lot of terms that under our assumption that that term has a sign. All the other terms you can recognize, most of them have a sign. I did say that I need a condition on the gradient of f, and it's because right in here I got that term, and I've got this thing, which is the inward bound curvature, and that's negative. So two negatives, two wrongs make a right in mathematics, and so that has a sign as well.
Where does the, so you, how do you infer stability?
Oh, well, you'll see, so right here, you look for the lowest eigenvalue of this thing. And then that is actually that gives you the perturbation of the area. I'm not sure if I've included.
I think in the original, like, you're just starting with the trap surface.
Yeah.
So why do you know that it's stable?
Oh, right. So here I'm assuming that I've got a marginally trapped surface. So I'm assuming, therefore, I'm assuming the mean curvatures. I'm assuming that both of them are non-positive. So it's an input assumption. that they're both non-positive. I guess you're right. I still need to you're right. I still need to assume that it's really outermost. Yeah. Yeah, I still need to assume that it's outermost, I guess. So so that there's none larger, and that since they do grow out to infinity, I think you're right. I need to assume that it's an outermost such. Okay. So the outermost is going to be
That's about flattening out the spaces.
yeah. I think I can also.
I also think these are asymptotically flat.
Yeah, I'm going to take asymptotically flat here. I could do asymptotically hyperbolic as well, I think, by putting in a lambda term in my mean curvature, but let's stick with flat for now. Okay, so I want to look at so almost all the terms there have a sign. That's sort of the main point, and just the leading derivative terms, and then they got that scalar. That's how you're going to control the topology, is you're going to keep this term in there and get a condition on everything else. So you need the first eigenvalue, which is to be non-negative. You need it to be non-negative. And of course, then the first eigenfunction is going to be strictly positive. So you have to look into that first eigenvalue and make sure that it's negative. And so I don't know how much I want to take you through it. For space-time dimensions, it is actually trivial because you can just write out that operator. Every term's got a sign, and then you've got the scalar curvature term. You can write that out as well, right in there. You get something that goes away when you integrate over a 2 surface, and you get another term which has a sign. Voila, you get the Euler characteristic, and you're done. No problem. Right. Straight integration. Yeah, there will be. Not today though. So 5 dimensions, you got to do more work, and I guess again, and I will have to go over this perhaps. But you let me see if I can give you the quick version because we're running out of time. Yeah, so you do have to do quite a bit more work. You have to reorganize this thing, and I've reorganized it here, put everything with a sign really into this thing called Q. Do a little bit of work. The main sort of point, and I know a calculation, nobody follows it, of course, on a slide like this, but the main sort of point is that you multiply by an arbitrary function squared. Now you're going to integrate that. So you can organize everything into terms of the sign, terms of the divergence, but that divergence has to come inside. And when it comes inside, you get cross terms. You get gradients of f and gradients of this. This is basically the first eigenfunction. It's e to the first, the log of the first eigenfunction. You'll get a gradient of psi. So you get grad psi, grad f. And so Cauchy-Schwarz will get rid of those terms for you in favor of terms that are d psi squared and df squared. And really, you have to do a little bit of that, and you get some funny factors in there. And I've got a 3 over m. It's basically because you have some freedom here. There's a lot of positivity going around, so you can trade one term off against another, and just enough to get rid of those nuisance cross terms, you get this. But you can do a lot better.
So Peter Paul refers to Cauchy-Schwarz epsilon.
Yeah. Yeah. And so that's where this thing comes from, but I'm sure I can do better. So there we go. You end up with this. We're not quite there yet because we have an extra term, but with a little bit more work, then a Rayleigh quotient argument gives it to you. And I've got it in here, but I don't think I really need to tell you very much or anything at all about it. Well, the main point is after a Rayleigh quotient argument, you now get yet one more function, which allows you to do a conformal transformation. And all you have to show is that you've got some metric of non-negative scalar curvature. You don't have to show that the one you started with has non-negative scalar curvature. And eventually you get there. So those technical details are practically pointless. If you do want to see them, I can, but maybe not in an audience. So just final remarks to close off. I've got an odd looking coefficient in think there's one remark that didn't make it to these slides, so I'll just scroll ahead until I can find my own version to make sure. That odd-looking coefficient can probably be got rid of, as I say, with better use of the Cauchy-Schwarz. Well, I can quite likely rule out everything except the spherical spaces. We just haven't got there yet. Black hole topology theorem. So if you want to, so the real goal, I think, at least here in this group, is to formulate general relativity on non-smooth spaces, and then black hole topology becomes kind of a moot point, because if you don't have a topological manifold, then how can you speak of its topology? However, understanding the dominant energy condition is not a moot point, even in that setting, because at least you can go back to the positive mass theorem, and you would still hope to have a positive mass theorem. Some notion of asymptotic flatness should still be all right. You be a manifold far away from, far out near infinity. And so the dominant energy condition, which also comes into play in the general positive mass theorem, is still worth understanding. And to understand it, you have to understand the scalar curvature. And so I think in the terms of this group here, you need a synthetic understanding of scalar curvature before you can go there. I'm done. So thanks.
We're gonna, after the question period, we're gonna take, I'm gonna take a seat to lunch, but are there questions or comments? And you're what, anyone who wants to join, just welcome to join us.
I think even in the space time settings,